Hello students, in this lecture we shall discuss about comparison of mechanical properties. The engineer usually cannot simply seek the forming process to suit his design. He must adjust the design separately for each particular forming process, and many factors actually influence this adjustment, not the least important of which are mechanical properties. Unfortunately, so many alloys are in use and their properties are affected by such a large number of variables. Basically, we are dealing here with shall be dealing here with metals and alloys. So alloys are our main concern. Although the final choice of the best alloy and the ideal process for any application may involve a considerable amount of practical testing, with the present survey of metallurgy as a background, the balance is devoted to putting such a body of information at disposal. Right, we can have several processes. For example, we can have sand casting. It is done mainly for cast iron and aluminium. We can have mold casting. We can have die casting. We have centrifugal casting. Forging. Rolling. Extruding. Cold drawing. Powder metallurgy. And electroforming. Now we'll first start with sand casting. Sand casting is done only for cast iron, and which has 33% or 3.3% of carbon, 0.7% manganese, 1.8% silicon, and the rest is iron. Or it can also be, this is the first one, or it can be also be done for aluminium, alloy, containing 5% silicon. So this is for the cast iron. The second one is now after doing it, we get a tensile strength pounds per inches of 32,000 for cast iron and 19,000 for the aluminum alloy. We get yield strength as 9,000. This is the unit, same unit. Yield strength of 9,000 for aluminum, and there is no yielding in case of cast iron, so there is no yielding. And elongation percentage in case of cast iron we get as 0.5, whereas in case of aluminum we get as 6.0. So these are the properties that are obtained by doing this mechanical process of cast iron. The second one is mold casting. And it can be done only in the case of aluminum, having 5% silicon, so we get a tensile strength of 24,000. We get a yield strength of this is tensile strength. We get a yield strength of about 9,000 as in the previous case, and we get elongation is quite high in this case, and we get an elongation about 9 elongation percentage. The next one is the die casting. Die casting can be done in case of aluminum as in the previous case, and we get a tensile strength of about 30,000, and we get an yield strength of about 14,000, high yield strength, and we get an elongation percentage of 7. Whereas die casting can be also be done in the case of zinc alloys containing 4% aluminum, 0.04% magnesium, and 1% copper, and the rest being zinc. So in this case we get a tensile strength of 47,000, very high tensile strength. We get yield strength, there is no yielding taking place, so there is no yield strength, and whereas the elongation percentage here is 7, as same as in the case of aluminum alloy. The next mechanical process is centrifugal casting. And it can be done in the case of aluminum and bronze. The only thing is that in this case, in the case of aluminum alloy, sorry, not in the case of aluminum, it can be done in the case of bronze. So it contains of 9% aluminum, 3% iron, and the rest is copper. This is the composition of bronze. So after centrifugal forging, we get tensile strength of about 88,000. We get an yield strength of about 32,000. and we get elongation percentage of about 40, very high value. High value of elongation percentage is obtained. The next mechanical process is forging. Forging can be done in the case of bronze and magnesium. So bronze again containing 9% aluminum and 3% iron, and the rest being copper. So forging gives tensile strength of about 85,000, gives an yield strength of about 34,000, and elongation percentage is 42, which is also quite high. So this is for bronze. Bronze it can also be used for magnesium alloy containing 3% aluminum, 0.3% manganese, 1% zinc, and the rest is being magnesium. So in this case, doing a forging will fetch a tensile strength of about 38,000. And yield strength of about 25,000, and it produces elongation of 15. The next mechanical process is rolling. It can be done for a magnesium alloy, (3% aluminum, containing 1% zinc and 0.3% manganese, just being magnesium. So producing a rolling gives a tensile strength of about 37,000, yield strength about 22,000, and elongation percentage 21.0. The next is extruding. Extruding again can be done in the case of magnesium alloy. This composition has been discussed. So it gives an yield strength of about 39,000, little more than the previous case. And sorry, it's not the yield strength, it's the tensile strength. Producing yield strength about 26,000, and elongation has been compromised here, and elongation is less. So if you compare, so these two values have been raised here, but the only thing is elongation has been reduced by comparing rolling versus extrusion. The next mechanical process is cold drying. Cold means the temperature is much lower than the melting point. Cool, that is why the cooled is being used here. Cold drying can be done in steel, stainless steel, containing 0.4% carbon and 0.8% manganese, and the rest is iron. So it gives a tensile strength, very high tensile strength of 115,000 and yield strength of about 74,000, and elongation percentage being 12. The next one is powder metallurgy. So powder metallurgy can be done on iron, pure iron, and it gives 35,000 as the yield strength, as the tensile strength, 25,000 as the yield strength, and elongation percentage being 7. And the last one is electroforming. It can be applied on nickel, which gives a tensile strength of about 110,000. There is no yielding taking place, and the elongation percentage is 16. So this is some comparison of the different mechanical processes applied in different alloys. So by looking at these values, the engineer can select which alloy to be used for any particular case.